Yeah, you can start actually.
Yeah. Mm. So, hi. Today, basically, we are trying to understand uh, more about network and what is subnetwork and VPC. So, initially, let's start with networking. Let's go and try to understand the basics of networking and how subnetwork is placed. And
Acha,
yeah.
are you presenting anything slides?
Yes. Oh, I'm very sorry. I think uh, sharing is stopped. Thank you for reminding me. So, can you
I can
can
see.
you can see the slides, right?
Yes.
Okay. Okay. So, agenda of today is there are two things. One is we're going to talk about network and networking basics, and also about subnetworking. Uh, what are public IP addresses? So, what is classful network, and what are CIDR, what are net mask, and all that. So this would be the first part. The next part would be all about VPC. So let's get started with the networking basics. Okay, so I'm just trying to you know go through some of the basic networking and sub networking, and let's understand now. So basically there are networks, and inside the networks there are sub networks. So those are basically you know represented with a set of numbers, saying for example 10.002.16 for a network, and something like 10.0.0.0.20 for subnetworks. If you see that subnetworks are uh, /20 here in both cases. So let's understand what this means. Okay, so with Amazon VPC we can create our own private data centers. So to effectively use the VPC, we need to understand the network and subnetwork address conventions. So basically these data centers are defined using CIDR convention. So CIDR is classless interdomain routing, and they are followed by IP address pattern and slash and a number. So for this whole exercise we are using IPv4 addressing as an example for simplicity, and it is applicable to IPv6 address as well. So let's understand how IPv4 addressing are constructed. It's a very I think we would have been using most of the time, and we know that it's a 32-bit address, and since it's a 32-bit address, we get theoretically the combination, we get somewhere around 4.29 billion addresses. So out of these 4.29 billion address, some are reserved. For example, some with starting all with zeros and ones, and some private address range uh, which are used internally, and some addresses which are used for broadcast and multicast are uh, reserved. So with all that, remaining approximately 4 billion IP addresses are known as public IP address. So this is the uh, pattern that we get as an IP address. So each number is converted into 8-bit notation, and there are 32 bits in total. So the maximum number that we can see here is 255, so which would be all ones in binary format. And if it is just one, um, it would be 7 zeros followed by 1. So public IP address are globally unique, and no two hosts can have the same IP address. So when when two systems are communicating, uh, irrespective of where they are physically located, we have to communicate between the two hosts. Hence, there both has to be globally unique, or any IP address has to be, any public IP address has to be globally unique to communicate. So challenges are now like uh, to route packets from one host to another host, um, because the destination can be in any part of the world, right? So uh, each address has to be stored somewhere to locate um, that physical location. So a better strategy should be used to identify each host based on the IP address. So let's talk about a little bit of history, how this was done earlier and how it is done now. So earlier they had used hierarchical address schema, and this address schema is was very similar to the postal system. So uh, whenever we write an address and drop it in the mailbox, we would write the continent, country, state, district, city, state, and building in a reverse order. So they would, first figure out which is, I mean, whenever the postal system goes from, receives the packet, it's going to check for the continent, then country, then down the hierarchy, it's going to, find out the exact location where the packet has to be delivered. In a similar way, a classical network or addressing architecture was used, and it was used from 1981 to 1993. And after 1993, a classless interdomain routing was used. So we will learn more about classless interdomain routing in a moment. So what are class based, earlier was a class based. So what is the class based addressing schema? So uh, basically the class based address schema was divided into 5 different classes. The first 3 class ABC was mainly for unicast, and class D was built for multicast, and class E was reserved for future purposes, which never came into picture. So what is unicast is like from one host to another host. So that one it's basically one to one mapping. So multicast is one to many mapping. Okay, so if you understand, probably you would have heard about broadcast. Broadcast is one to anywhere. It is different from multicast. So try to understand, multicast is from one uh, host to multiple hosts, but they are defined. In broadcast, the receiver end is not defined. Okay, but in the unicast, it is something like from one host to another host. So we mainly deal with these unicast. So Let's go and understand what are those class ABC. So before we start the class and try to understand class ABC, let's understand how classful network routing was done. Okay, so there basically IP address was divided into two parts. The first part was destination network, and the second part was the host machine or machine in the network. So whenever the packets had to be delivered, the packet is delivered to the destination network, or destination network can be an organization or a bigger network where hosts are located. So the organization that owns the destination network is responsible for internally routing or delivering the packets to the host. So routing became very simpler, for classful network routing. In class A network, how would you identify? So there, this is the IP address, and how would you identify whether it belongs to class A or class B or class C? Was the first bit always started with 0. Okay, so I'm I'm sorry, Anil.
Continue, Achal. Continue.
Yeah. So the most significant bit of IP address in class A networking is 0, and followed by 7-bit of you know numbers, 7-bit which identifies the network. So the remaining 24 bits identified the host machine inside the network. So class A in overall had 127. So all it was very less in number, but it had got 16.8 million possible hosts. So under this, there could be 16 million and odd possible hosts. So this identifies the first 8 bits identified the class A network. So class B network was, you know, identified by the first 2 digits. I'm sorry, there is a typo here. I have to change it. So the first 2 digit 10 uh, was used to identify the class B network, and remaining bits were used to identify the actual network itself, or the organization. The next 16-bit, I'm very sorry, the next 16-bit was used to identify the host. So in overall, there were 14 bits to identify the network itself, and remaining 16 bits to identify the target host. So if you do the math right, so there were around 16,000 possible class B networks um, that were available, and each of these networks could have 65,000 possible hosts. And when it came to class C network, the first 3 digits were used to identify class C network. So the most significant bit was 110 there, and the remaining 21 bits were used to identify the network. If the first 3 bits was 110, the 21 bits were used to identify the network. That's how the class C network was used to calculate.
Achal, like for all C type of networks,
Mm-hmm.
it will always start with 110, right? Then only they will identify the itself the C network.
Exactly. So when it start, if you see the previous example, it starts with 10,
Yeah,
and
10 means
Yeah, it's a class B network. And another thing, another one, I mean, if it starts with 0, it is class A network. So in any case, it would not any no other IP address would start with which belongs to a different class would start with 0 bit. Okay, so
So remaining all things in network, right? Remain rest of the things.
yeah, so if the most significant bit starts with 110, then it would take another 21 bits to identify the network. Okay,
Got it. Got it.
so the remaining 8 bits which are there were used to target the host. So there were 256 possible hosts that could be connected to this network, but there were 2 million class C networks available. So these class C, when I say 2 million, these are 2 million organization could own this class C network. That's what it means. And each organization could have 256 possible hosts. So if a company is having 20 people or 250 people, then or 250 possible hosts, then class C network was assigned. If a company has more than 256 or 255 possible hosts, then class B was assigned. And if a company has more than 65,000 K, class A was assigned. That's what it means. So let's understand the networking issues related to these classes. Okay, so class A was super large. Basically, this was suitable for any ISPs, that is internet service providers, and governments, which had nearly 16 million hosts. And class C was too small for companies, which was somewhere you could, even though it says 256, you could actually use 251 approximately possible hosts per network. If 250 hosts, you mean if the company exceeds 250, multiple network blocks were provided, which actually led to the growth table where sorry, it actually led to the growth of the route table. So if there were more than 250 and somewhere around 500, let's say there were around 500 hosts, uh, a company was provided with class C, and two route table entries were made for that company. So whenever the you know whenever the IP address comes with the class C range, then it would go to the route table, check for the possible class C network uh, organization, and it would be routed to that. So class B was medium size companies. It was class C sorry, class B was allocated to medium sized companies, which could hold up to 65,000 hosts. And where the class A was too big and class C was too small. Okay, so this actually, let's say companies which had somewhere around 2,000 or 5,000 hosts was allocated with class B, but some of the hosts were basically, there was a wastage of address space. So this led to the rapid exertion of class B address space. And because of this, IPv6 addressing was comprehensively devised, and it was addressed. I mean, this particular problem was addressed through IPv6. But around 1993, they came up with a different approach which could solve this problem, wastage of address space, uh, and they tackle with an approach called CIDR, that is classless interdomain routing. So this is basically the current method for allocation of IP addresses and IP routing. So this is more flexible, and it conserves address spaces. The problem what we had with earlier with class B, where there was wastage of address is addressed in classless interdomain routing. The allocation of these address spaces was basically based on the organization actual needs, and they could be added, or the growth in the required address space was handled gracefully. Okay. So number of bits used to identify the network is explicitly used with slash and a number notation. So this is a typical example of cider block. So basically what it means is this the first part identifies the network, and the another 16 bits identify the host. So in the second example, you see this first 20 bits identify the network, and remaining 12 bits is used to assign the uh, address the host.
So Achal,
Yeah.
then what goes like slash 20 we have read subnet. So where it goes with 20, how they will be
Yeah, probably in the next slides you would get a better idea of what it
Sure.
means. Okay.
Sure.
So
First
basic
part is network, next part is host. That's what I understand.
Yeah. So basically, what you need to understand is that uh, when you say slash 20, so 20 bits are assigned for the network to determine. So this is the whole of network, and the remaining is basically can be used for hosts. That's what it means. So this slash and a number explicitly says, this number explicitly says the network size in terms of bits. Okay. So when you say 32, okay, it basically means the host itself, because we have got 32 bits in nature, and all is used to identify the host, instead of network. So uh, if you say 20, this till here it was used to identify the network, and remaining was used as host. But when you say 30, it comes 32 when it comes uh, till 32 bits, right? So the whole range of bits are used to identify the network. uh, identify the host. So let's understand what subnet is. So subnet is a short form of subnetworks. So networks is subdivided into subnetworks inside an organization. So why we do this is because it is for ease of manageability, security, and isolating to isolate the network, and so forth. So CIDR block is used to identify these subnets. So in the previous slide we saw, whenever we say that slash 20 is representing CIDR block, that we're gonna see in the next slide. So VPC requires you to specify network and subnetwork using the CIDR blocks. So you can control how basically subnet communicates with each other, and how it can control how it can communicate with the outside world, which means internet, with the help of internet. um, so we can when we create a subnetwork, we can actually create fine-grained security policies around these subnets, and we can add firewalls and isolate them from doing certain set of actions or communications. So I have also added AWS public IP ranges. This actually shows the different IP ranges for each services. I'm not gonna uh, go through that, but I have added this link in case you want to see that IP ranges for each service. So this is an example of subnet. So let's understand there is a network here. So network starts with 193.293.239.32.0/20. So this is /20 is the network space, and we want more subnets in it. So we divided the subnet into 4 parts. So how we're going to do that is by taking these CIDR range up to /22. So when you add /22, when you increment this CIDR block, you get a different subnets within the network. So in this example, we have taken /22 here, and since we have taken /22, I have given binary representation of /20 and /22. So /20 is till here, and the highlighted ones represent /22. So when we want to have a 4 subnets within the network, we're gonna add one to each one of the blocks. So we got 0 0 0 1 1 0. It is just we are adding 1 to these binary numbers, and what this means is 0 1 2 and 3. So when we add that, we get this IP ranges for /22 subnets. So with this, you get with the remaining 10 um, uh, uh, 10 bits, you get around 1024 hosts, but 5 hosts are reserved by um, AWS, and you can use that. So you get possible hosts like 1019 hosts. So you can actually there is a subnet calculator here if you want to identify how many bits we need. Let's check how it works, and let's see. So let's say we have a CIDR range, some CIDR range of 10.0.0.0.0, and bit mask is 20. So there are maximum of 4096 subnets you could create, and let's say you want only 4 subnets in this. So if you want 4 subnets within this, there are 30 you need up to 30 CIDR blocks. So this is just an example of so let's see how much. So when we tried this 22 CIDR blocks, we can see that there can be 1024 possible hosts. Um, this is a helpful tool if you want to identify how many hosts you want to have. And anyways, this is a general understanding of how network and subnet works. And if you come to AWS, there are more restrictions to subnet creations. So we're gonna go through that in a bit. So we understood, basically the public IP address. So let's understand what private address space means. So private address space are basically reserved address space for internal use only. So they are, they rest behind routers or NAT devices. So you might be wondering what NAT device is. So we're going to talk about NAT device as well, the future part. But basically, private address space are reserved address spaces. So they cannot be used for public address. Okay, so if you see these address space or these three address range are reserved for private address. So they rest behind the routers. So any internal networks will have these IP addresses. And there are few more addresses which are reserved, as I told earlier. So this is a very common address. So this is basically says a loopback. This is called a loopback address, where whenever this address is hit, it will loop back to the same machine. So whenever you type this, it basically means the local host. So what does 0000 means is that it also means a local machine, but it also means there is no a particular private address. So it means any IPv4 address or all IPv4 address. It's a generic IP address. So if you use this, it means that it can match to any network address, because when it is and operated with the net mask, you would get the same value. So let's understand what net mask means. Okay. So basically, net mask or network mask is about identifying whether this particular IP belongs to our network or not. Okay, so we use a simple technique of bitwise AND operation. And whenever you do a bitwise AND operation with these number with the network, or sorry, I'm very sorry, with the you know with the IP address, and if the number turns out to be the network address, it means that it belongs to the network. So in this example, we have like network with /20, which means that 20 bits has to be 20 bits will identify the network. So all of the 20 bits are set to 1, and remaining bits are set to 0. Let's see an example, how actual example how it works. So I have taken our network is 193.239.32.0/20. So our since this is 20, we are saying 20 bits is used to identify our network. So the mask, when we write the mask in a binary format, it would be in this format. All the 20 bits with 1 and remaining with zeros. And when you bitwise AND with the IP address that we are trying to find out whether this particular IP address falls into our network, when we do the bitwise AND, we would get a result here. So this result should be same as the network that we have. So if it matches the network, then we can say that destination machine is part of our network. So this is how we identify, whether a particular IP address is part of our network or not. So whenever a network is given an IP address, and if the network wants to find out whether this IP address belongs to our network or not, it is done through this bitwise AND operation and found whether it belongs to the network or not. So this net mask is basically can be applied to any network. It can be a network or sub networks, and it can be any network range. Okay. So till now we basically understood the very basic of you know networking. I hope you have understood. If you have any questions, Anil, Sridhar, we can stop for a minute.
Yeah,
And,
no questions from my side also. You can proceed.
okay, since Sridhar is traveling, I'll just move on. So let's now try and understand what Amazon virtual private cloud means. Basically, it's a private network in AWS cloud. Okay, so we're going to understand. The agenda of this virtual private cloud is we're gonna basically understand what VPC means, what default VPC means, what is custom VPC that we're gonna create, and what is VPC, what are VPC networking components that are available, and what are the VPC security components that are provided. And we are also going to go through like the data flow of public subnet and private subnets, and at the end we'll understand how the hybrid architecture is built for the VPC. So let's understand what is VPC. So virtual private cloud is, it's a prime example of software defined networking. So what is software defined networking is the whole of the network is defined using a software. So it is not hardware determined like earlier. So the whole is a virtual network. Okay, so um, in on-premise data centers, there would be, basically typically how it works is there will be a network admin to configure the networks. But in AWS, as a admin or as a user, you got to do it all. So you got to define the virtual network, um, and so VPC is basically a virtual network dedicated to your account. So you can play around with this network, and it is completely isolated from a network from different accounts. Okay, so basically they are logically since this is a software defined network, they are logically isolated from other virtual networks. And we can select either IPv4 CIDR block or IPv6 CIDR block. So if you choose IPv6, then there are certain virtual components which still doesn't support IPv6. We're gonna talk about those components as well in the future part. So If you want to understand the tenancy of the VPC, it can be default or dedicated VPC. So what it means is the whole network is dedicated to you alone, and default is basically you will have that network shared by others, but though they are logically isolated, they can be shared. So if you want a network, a location which is dedicated to you and not just logically separated, you can go with dedicated option, and there is all the resources which comes under this tenancy would be dedicated to. So if you are deploying any EC2 instance, that would be a dedicated EC2 instance. So this VPC will have subnets. We can create subnets under VPCs, and these subnets can be private or public subnets. And there are a lot of components, networking components, which you can configure under VPC. For example, some route tables, firewalls, internet gateways, NAT gateways, or VPC endpoints, and there are many more networking endpoints, networking components that we're going to discuss now. So basically, you can make VPC an extension of your on-premise data centers using VPN. So basically, this is a hybrid architecture what we are talking about. So we're gonna see how you're gonna achieve this in the later part of this session. So let's understand some region and availability zones, as how they are related to VPC. So in previous session we understood how regions are created, and how availability zones are created within the region. So when it comes to VPC, so VPC spans across all availability zones in that region, but VPCs are region specific. Okay, so as soon as you create a region or you have an account, a default VPC is created for each region. So whether you're gonna create this VPC or not, so whether you're gonna create any VPC or not, there would be a default VPC created for you. Though you can delete this VPC, but by default this VPC would be created. So default VPC network CIDR range starts with 173.31.0.0/16. This is standard across any region. So as and when you create, as and when you have an account in any region, for the default VPC, this would be the a CIDR block assigned, and each availability zone will have one public or one default subnets as well, with these CIDR block range. So these are created by default. So these public subnets are default subnets which are created. So let's understand what custom VPC means. Okay, so basically custom VPCs are any VPC other than the default VPC. Okay, so they can have as many subnets as we want, in each availability zones. Okay, there is a limit of 200 though, but yeah, you can create multiple subnets. So some subnets can be configured as public and some subnets are configured as private. So let's understand probably in a later part what is public subnet and private subnet. So VPC is configured with IPv4 as primary addressing scheme. So if at all, if you need IPv6 addressing, then we have to optionally enable that IPv6 addressing scheme. Once you enable IPv6 addressing scheme, any instances that you create under that subnet would get both IPv6 and IPv4 addresses. So let's understand VPC components. Yeah. So the first component what we can understand is the subnet. So basically subnets are isolated segments of VPCs, and the next component that we can talk about is the route table and the router. So these route table contains a set of rules called routes. Okay, so they are basically used to determine where the network traffic from a subnet is directed. Okay, so basically it is a table which says where the network is targeted to, and there are routers which are created in the VPC which would actually use this network table and route the traffic to required target. So there is something called as elastic IP and elastic network interface. Elastic IP is basically a public IPv4 address which is uh, reachable anywhere from the internet. Whenever we say public IPv4 address, it means that it can be that particular address can be reachable from the internet. Okay, so we can associate this elastic IP address with your instance, to enable the communication with the internet. Uh, but currently, elastic IP address doesn't support IPv4, IPv6. Sorry. And elastic network interface is basically a logical networking component in a VPC. It's basically represents a virtual network card which is connected to your instance. So you can create and configure these network instances and network interfaces in your account and attach them to your instances in your VPC. Okay, so basically one elastic IP address is attached to one private IPv4 address. So why do we need this elastic network interface is that as and when we attach elastic IP address to instance, if the instance goes down, then we have to go and manually configure the switch over between um, elastic IP address to that instance to a new instance. But if you are connecting elastic IP address to the network interface, and the network interface is connected to the instance, if the instance goes down, we can just connect the elastic network interface from the down instance to a new instance, carrying all the attributes which are set to the elastic network interface. So basically that's the reason why elastic network interfaces are used. So there is a virtual device called NAT gateway and NAT instance, and these are basically um, this basically help, like if the instances are part of private subnet and they want to connect to the internet or any AWS services, uh, this NAT gateway or NAT instance will help to direct that particular traffic to the internet. So what we need to understand here is if any instance are part of a private subnet, right? So those instance cannot communicate with the outside world. So the anything which resides in the private subnets are restricted to communicate out to the outside world, but it can communicate within the VPC network. Right? So we need a NAT gateway, a NAT instance to communicate to the outside world, and these also restricts um, inbound requests. This allows only outbound requests. So this NAT gateway uh, are like available only for IPv4, and the difference between NAT gateway and NAT instance are like a NAT gateway is managed by AWS and NAT instance is customer managed, and there is a lot more monitoring and maintenance to be done from for NAT instance. So the next component that we can talk about is security group and network ACL or network access control list. So security groups are basically both of these components are virtual firewalls, and security groups are part of they are for the instance attached to instance, and they are at the instance level. And network ACL is an basically it's an optional layer for security, and it is used for used at a subnet level. So these are connected to the subnets, and next component is internet gateway, and these are components which are used to communicate, which actually bridges the communication between instances and the VPs, instances and the internet. So these components are highly scalable, highly available, and redundant in nature. So they do not add any latency uh, in the network. That's what AWS claims, and there is also another a kind of internet gateway which is called as egress only internet gateway. So we need to understand the term egress here. There are two terms called egress and ingress. So egress is outgoing calls. So anything, uh, if a request is made from within the instance or within the VPC network, and if it is going outside the VPC and towards the internet and comes back as a response, this is basically called egress. And ingress is a regular uh, call which comes from the internet to the resources in the VPC and responded back to the the instance, sorry, the host which requested. So Egress only internet gateway means it allows only outbound communication, and it prevents all internet initiated requests. And why do we need such kind of gateways is because um, if we have a database instance, and we need these databases to connect to uh, different services which are available, but you don't need those services to directly contact a database instance, then we would use such gateway. And this egress only internet gateway is applicable for IPv6 only. So basically there are to establish a VPN connection, uh, we need to there are many options that are available. So to understand what VPN connection means is, uh, it's a secure connection between your on-premise remote network to your VPC, right? So if you want to connect between your on-premise system to your VPC, you have an option of VPN, and this VPN is a secured connection. So the protocol would be IPsec, that is IP secure. So there are many options available in this VPC connections. So to name it, uh, that is AWS site-to-site VPN, AWS client VPN, and AWS VPN Cloud Hub. So we're going to go through all of this this session. So uh, let's understand VPN connection better in the future, in the later part. So what are these flow logs? So flow logs are part of security feature and also monitoring feature that is provided by VPC. So any request which comes, any traffic, IP traffic that is coming and going from the VPC network is captured in this flow log, and flow log has to be explicitly enabled, and we can direct the captured information to different destination, for example S3 or CloudWatch logs. And also there is something called as a peering connection. This is basically you can connect between two VPC networks, and you can make both network or resources inside this network communicate using private addresses. Now, so if there are two VPCs, and if they are not peered, both any resources within those VPC has to communicate through internet gateway. So if you have two services, if you have two resources within two different VPCs, and since you want to communicate between the two resources, and you don't have to go through the channel of internet, you could actually use this peering connection and connect between these two VPCs, and obviously it would be under AWS network, and it would fetch some performance for you. So these there is something called as endpoints, and these are basically like which enables you to privately connect your VPC to AWS services. So there are two different kinds of endpoints. One is gateway endpoint and interface endpoints. So we're going to check that the later part. So There is a private link component, which private link actually provides private connectivity between VPC. So basically, for peering connection and all that, uh, we use private link in the backend. So there is something called as AWS Direct Connect. So this is also part of hybrid architecture, where you connect, where you want to connect your remote data centers into your VPC, and you don't want to take the route of internet, and you want a dedicated network, which AWS provides. Then you go with this direct connect facility. So those were the you know VPC networking components, which we addressed very briefly. But let's try to understand those components in some more depth. So the subnets are now basically there are two types of subnets. One is public subnet, and another one is private subnet. So to determine whether a particular subnet is private or public, uh, you got to see the routing tables attached to it. And any public subnet which has a target of internet gateway is basically a public subnet. So subnet with internet gateway attached is a public subnet. And if you have a private subnet and you want to connect to an internet, earlier we saw a virtual device called NAT gateway, and uh, you can actually see that here a database is connected to router, and this has a NAT gateway, a target. So this would route to the NAT gateway, and NAT gateway would send the request to internet gateway, and the internet gateway will send the request to the internet. So basically, there are two kinds of subnets that you need to understand. Public subnet is internet accessible whenever you need internet access. You create a public subnet. You create a private subnet when you don't want to you don't want internet to connect this network, and you want to secure this network, and from any instance within this private subnet can access any network within the VPC using private addresses, right? So this is all about public and private subnets. I hope you got it. I hope.
Yes.
So let's understand subnet and EC2. Okay. So as soon as you launch an EC2 instance, private IP address is assigned based on the address range of the subnet. So there can be option where you want to choose whether you want public IP address or not, but private IP address is assigned by default whenever you create an instance within a subnet, and that private IP address would be in the range of the subnet. So this any IP address which is assigned, a private IP address which is assigned to EC2 instance, will be till you terminate the instance. So even if you stop the EC2 instance, this private IP address will still be there as part of the EC2 instance. Whereas if you assign a public IP address, uh, to an EC2 instance, and if you stop the EC2 instance, and public IP address would be released. And as and when you start the EC2 instance, a new public IP address is assigned. So for the default subnets are basically, we saw that, right? So we have a default VPC and we have got default subnets. Default subnets are configured to issue public IP addresses. So basically these default subnets are public subnets. Okay. And public IP address is assigned from AWS own CIDR range, and you cannot, as a customer, you cannot choose what public IP address needs to be assigned to EC2 instance, and basically those are at the full discretion of AWS on CIDR range. Okay. So we understood how the EC2 and subnets are related. So let's understand how route tables, what route tables are, and some key concepts about route tables. So route tables contain basically a set of rules. Basically they're called routes, and they determine the network traffic from your subnet. So basically there are two parts to that route table. One is destination and another thing is target. So when you say 10.000/16 and target as local, any CIDR block within this range will be can actually communicate within the VPC. The local means within VPC. Okay, so you can also if you can see the second entry, this is all about the IPv6 address CIDR range, and you need to have a separate entry for the IPv6 address CIDR range as well. So both are both has to have two different entries in the route table. So there is an entry for this CIDR block, which has basically connected to a peering connection device. So this actually means a peering connection device, and for private IP address, it is for any address which is IPv4, it is routed to internet gateway, and any address of IPv6 is directed to egress only internet gateway. So basically IPv6 address are globally unique, so you don't need an internet gateway for communication. So what this means is that any IPv6 address has to go through egress only internet gateway, which means that there can't be an access from the outside internet to the instance, but there can be an access from the VPC or a subnet towards the internet. So the key concepts are like main route table. We need to understand what main route table means. as and when the VPC is created, main route table is created, and it is associated with any subnets that you create. You can also create a custom route table, and these route table are basically uh, you can assign it with any subnets that you want, and if subnets are not assigned with any route table, or you have created a custom route table and you have detached from the subnet, then subnet automatically points to main route table. So route table association is what we discussed right now. So basically it's an association between route table and the subnet. So destination is basically the CIDR range of the subnet. Target is basically where the traffic should be routed to, or which is the endpoint, or which is the target for the subnets. So in the above example, we saw the target could be uh, within the VPC network, or it could be to the peering connection, or it could be to the internet gateway, or it could be the egress only internet gateway. So local route is a default route for communication within VPC. This is what is local route. So let's understand what elastic IP means. So basically elastic IP is a static and public IPv4 address. It can be associated with with your instance or network interface, as we discussed earlier. The advantage of associating elastic IP address with network interface is, or instead of directly associating with instance, is we can move all the attributes of the network interface from one instance to another instance within just one single step. So if we have 5 different IPs associated with the network interface, and the network interface is associated with the instance, and within a single step we can move all the attributes of that network interface to another instance. And also mentioned earlier that currently AWS does not support um, elastic IP address for IPv6, and elastic instance can access internet through by doing 2 steps. One is it has to set up a route entry for internet gateway, and it has to have an public IPv4 address or elastic IP address or IPv6 address. So these are the two things that is required for EC2 instance to communicate with the internet. One is a route entry for internet gateway, which we saw previously in the slide, right? So another thing is elastic IP address, or any public IP or IPv6 address assigned to EC2 instance. So your account basically is limited to 5 elastic IP addresses, but it's again a soft limit. You can ask for more if you need it. And there would be they would impose hourly charges for uh, elastic IP address, as they are expensive. uh, One elastic IP address is free if you have associated that with an instance which is in a running state. If not, if the instance is in stop state and elastic IP address is still attached to it, and that elastic IP address is charged as well. So the takeaway is like you have 5 IP address given to you. One is free if it is attached to an instance which is running. Other four are chargeable whether you have attached to uh, your instance or not. So all this IP address are basically you need to um ask for it, and AWS would provide. So they are not there as soon as you create an account. You have to uh, you know ask for the elastic IP address, and then the hourly charge is applied for that. Um, I would request you to give me 2 minutes. I'll just not even a minute, just a minute. I will just take a sip of water, if you don't mind.
Sure.
So yeah, I'm back. So let's understand what NAT gateway and NAT instance mean. So there are instances where we want um, private subnets to talk to the internet, and we can do so using NAT devices. All the outbound traffic is directed to NAT gateway with an entry in the route table, and basically NAT gateway scales automatically according to our needs, and these are basically managed by AWS, and uh, it is provisioned in public subnets, which means that it will be placed in the public subnets, which actually be part of one single availability zones. So if you need high availability of it, then you're gonna deploy it in all three availability zones, and it will be chargeable for uh, all the availability zones. And so if you have three availability zones and you have created three NAT gateway instances, NAT gateway, then all the three NAT gateway device, virtual device, are charged. So a NAT device has an elastic IP address already attached to it, and is connected to the internet through internet gateway. So again, NAT device doesn't support IPv6 traffic. Um, so if you need a similar feature, then for IPv6 traffic, we got to use egress only internet gateway instead. So NAT instance has a very similar capability of NAT gateway, but this is basically a customer managed NAT instance. So you got to spin up a regular EC2 instance, select the NAT instance AMI, and you need to apply the security patches or software updates all by yourself. And same goes with the availability here as well. So you got to deploy, uh, if you're expecting high availability, you got to deploy these instances in all availability zones. So you got to handle scalability and throughput issues as well. So if there are if you see there is a throttle in the request, then probably you have to move uh, these instances to a bigger instance. And these NAT instances and NAT gateway are though they are similar in nature, they have subtle differences when it comes to AWS managed and customer managed. So I have attached a link here. Please go and check that. It has a detailed comparison between NAT gateway and NAT instance. I've just added few instance sorry comparison which are very common in nature. So basically in terms of high availability, uh, or how it differ from NAT gateway, NAT instance, and maintenance, and also the cost. The cost is something which matters a lot when you are choosing between NAT gateway and NAT instance. So NAT gateway are charged depending on the usage and duration of usage, and also the amount of data that is transmitted between the or sent through the NAT gateway instance. But when it comes to NAT instance, it is basically charged based on the duration. It's like regular instance charges. So there is a cost optimization or cost saving if you're going with NAT instance, but you got to bear all the manageability risks and scalability risks. So there are, as I said earlier, also there are more detailed comparison. Please go ahead and read that as well. So earlier, as I said, there are two different firewalls which are provided by VPC security. One is security group and another one is network ACL. So security groups are basically at instance level and which are within the subnet, and these security groups are stateful in nature. What it means is whenever there is a whenever you have written a rule inside this firewall, and if it is an inbound rule, and if a request comes from the internet and the response is also valid for that inbound rule, and it same goes with outbound rule as well. So if there is an outbound rule saying that instance can talk to a particular resource which is outside in the internet, it will, if the request is allowed, response is allowed as well. So basically that is called a stateful nature of a firewall. So you can specify allow rules for the security groups, but you can't or there is no option for you to deny any particular rule. So here you can just say what traffic can be allowed, and you cannot say what traffic cannot be allowed, but you need to handle it gracefully through the allow rules only. Okay, so there can be 5 security groups attached to an instance at a time. So these security groups can actually point to other security groups as well. So uh, the security group values are the CIDR. It doesn't need to be just the CIDR block. So if you don't specify any security group when you're launching an instance, so a default security group is associated with the instance. If you see this diagram here, you see an instance one is attached to a security group here, and the same another instance also is attached to the same security group. So multiple instances can attach to a same security group, and also multiple in single instance can have multiple security groups as well. And there is also an option of security group you know linking to another security group. So what happens with that option is, let's say this is the instance that we have connected to security group, and this is also another instance connected to this security group. If one of the security group has a link, has been associated with another security group, then instance of this instance 1 can actually access instance 2. So anything under this security group will have permission to privately access the other instance under the different security group which is associated. So yeah, so that is what basically probably we need to understand in terms of security group. Let's understand what is network ACL. So network ACL is also, as I said earlier, it is optional layer of security for firewall of VPC security. So they are associated with the subnets rather than any instance itself. So they can only you can associate you know with multiple subnets, but at a time only one network ACL can be associated with one subnet. So one network ACL can be connected to many subnets, but one subnet can be connected to one network ACL only. So these are stateless um, firewalls. So basically what it means is you need to mention both uh, allow and deny traffic. I'm very sorry, you have to set both inbound and outbound traffic. And now what it means is, if you mention in inbound traffic that I will allow this particular IP range, and in the outbound traffic you have to also mention that that particular IP range is allowed. So uh, you whenever you're making some restrictions within this stateless firewall, you got to do it in both places, that is inbound and outbound. So these inbound outbound rules can either allow or deny traffic. So this has got an option to allow or deny a particular traffic, which is not possible with a security group which has only allow traffic rule. So this diagram basically depicts the how the network is, uh, the architecture of the security firewall is constructed. So you have internet gateway, then router. Router has the router table. After the router table comes the network ACL, then comes the security group, then comes the instance. So in the future, architecture diagrams, you wouldn't be seeing this network ACL and security group for brevity, but uh, these are always present in any network that um, uh, that are present out there. So um, it might not be represented in the picture, but it always exists in between. That's what I mean. So there are a few comparisons between security group and network ACL, you can actually there's a link attached to this thing. You can go and find out more about it. But on a very on a high level, you have to know that security group is at instance level and network ACL is at subnet level. So um, network ACL is at a broader range. So security group is at each instance level. Okay. So and security group has only allow rules, and network ACL has both allow and deny rules. Security group is stateful in nature, and network ACL is stateless. We evaluate all rules before deciding whether to allow or not. And one important um thing to remember is these rules are processed in a numerical order or ascending order in network ACL. So if there are rules, let's say in rule 100 to allow all traffic, and in rule 200 if it says deny traffic, the denied rule is overridden by the 100th rule, which says allow all traffic. So that is something which you have to keep in mind when you are constructing you know a firewall. So this security group applies to an instance only if someone specifies the security group when launching the instance. Okay. So these are basically associated with instance. This can be associated with instance later on as well. um, and network ACLs applies to all instances in the subnet. Okay. And it is associated with different security groups as well. I mean, it just acts as an additional layer for it. So we understood what those firewall are represents, right? So basically, subnet subnet firewall was for instances, and network ACL was for subnets. So going forward, imagine that those would be placed here when instance is communicating to uh, a router. They would be placed one within the subnet and one outside the subnet. Okay. So let's understand what internet gateway means. So internet gateways allow communication between instances and instances in within the VPC and the internet. So as the name itself suggests, it's a gateway for communication between VPC and internet. So these are highly scalable and highly available, and also they are redundant in nature. So these are not managed by you, but they are completely managed by AWS. So you don't have to doubt their scalability or high availability nature. So basically internet gateway serves two purposes. Okay. So those are like they provide a target to your VPC route tables. Okay. For basically to route the traffic to the internet, and also they perform sorry to perform network address translation for your instances um, that have been assigned public IPv4 addresses. You need internet gateway. What it means is whenever uh, you know a request comes from the internet to the internet gateway, Internet gateway has to do the network address translation from public IP address to private IP address. So all your devices within the VPC are having the private IP address, and those has to be matched with public IP address. So internet gateway does the task of network address translation, and respective request or traffic is routed back and forth um, with between internet and the instance itself. So how do we enable to access internet, right? So let's go through the steps to do that. So let's attach a internet. We have to attach an internet gateway to your VPC. As soon as you create a VPC, internet gateway would be created. You can also delete internet gateway if you don't need it, but uh, by default it would be created. Okay, so ensure that your subnet route table points to the internet gateway. So this subnet has make sure that if you want this subnet to communicate, or instances within the subnet to communicate to the internet, you have an entry of the internet gateway in your route table. So as soon as you make this entry into the right route table, this subnet is a public becomes a public subnet. Okay, ensure that instances in your subnet have globally unique IP addresses. So basically, if you have uh, IP public IP address or elastic IP address or IPv6 address, you can communicate with the internet, or else you can't communicate with the internet at all. So once you have attach this internet gateway within the VPC. You have created an internet gateway with the VPC, and you have made an entry into the route table. Then you should see to that your EC2 instance has elastic IP address attached to it, or any kind of global unique IP address attached to it. And also you need to make sure that your firewalls have respective privileges to allow the traffic, or basically what it means is network ACL should be having a particular rule which will allow the traffic for the internet, and security group rules should also have a relevant rule to allow the traffic. So internet gateway supports both IPv4 and IPv6 addresses. So if you allocate an IPv6 address to an instance, it can communicate with internet gateway as well. So egress only internet gateway means, I think we already discussed that earlier. It is very similar to internet gateway, but it would allow only outbound traffic towards the internet, so to and fro from the internet. Okay, so and it is specifically devised for IPv6 traffic only. Again, these egress only internet gateways are managed by AWS, hence they are highly scalable, highly available, and redundant. So the same rules applies to egress only internet gateway as internet gateway. You need to add a route table entry for the device itself. So internet gateway ID has to be part of the target in the route table. So again, egress only internet gateway is also stateful, which means that any request which goes doesn't need the permission to come back, or there is no restriction. Response is not uh, monitored, or it is not filtered. Yeah. So let's understand uh, what VPC flow log means. So basically, VPC flow log are feature which lets you capture the information about the IP traffic, which is coming to the VPC or going from the VPC. So you can publish the traffic or the information to CloudWatch logs and Amazon S3 devices, S3 bucket. The flow logs are optionally enabled, so you need to manually enable the flow logs if you need it. So basically this can help in diagnosing uh, the security group rules and monitoring the traffic. So let's say if you have you know a restrictive security group and you are not sure why the request is not coming to the instance, you are filing the request but it is not reaching the instance at all. So you can actually go through the logs, these logs, and find out where um, it was stopped, right? So whether it was accepted, whether it was rejected, um, and so forth. So basically you can actually capture all the traffic, whether it's accept or reject, and you can also capture based on only accept or reject. So if you just want a reject traffic to be captured, and which in turns reduces the size of the log data, it can be done as well. So you can also create flow log for your VPC subnets and network interfaces, the separate log. So the data that comes out of this flow log are called flow log records, and they usually contains five tuple in the sense uh, uh, five data points which are important for us to understand or us to monitor. So those are like source address and source port, destination address and destination port, and the protocol which was used for this um, traffic. So I've also added different protocols and their numbers. You can just check that link as well, which will give you an idea of what port 22 means, or what would be the port for SSH, things like that. So here is the syntax of flow log record. So mostly we would be interested in these patterns, these source address, destination address, source port, destination port, and the protocol. So you can see that here. So for the accept protocol, you have accept record, you have source IP, destination IP, their port numbers, and the protocol which was used. And this is if there was no data, if it was skipped, it's an example of how it looks like. So briefly, let's just try to understand the actual what inbound call means and how it flows through, how the data flow through the VPC. So this is a very important aspect of understanding how the data flow through the public subnet. Okay, so basically. Requester for website sends the request to our public IP address. So we have a public IP address. So the requester knows that public IP address, and he basically sends a request for that public IP address, and it is routed based on DNS servers and all that, and it comes to AWS network, and it hits the internet gateway. Internet gateway receives this request, and it looks up the table for that public IP address. As I told earlier, it would do the network address translation, and corresponding IP, private IP address is attached and sent to the router. Okay. Internet gateway basically, as I said, forwards the request of EC2 instance IP address to the router, and router in the router table specifies where the traffic should go to. It would identify where the instance belong, or which or to which subnet the instance belong. So router would check the based on the CIDR block of the subnet. It would route the traffic referring the route table. So once it is directed to the subnet, uh, it would be checked by network ACL, and it would inspect the request for allow and deny rules. uh, and since this is an inbound call, it would check the inbound rule, and if the request is allowed, then the security group associated with that instance will also inspect that request. If the security group allows the request, then it reaches the EC2 instance. Then EC2 instance processes that request and responds back, okay, in the reverse order. And EC2 when EC2 responds back with let's say a web page content, since the security group is stateful in nature, it automatically allows the response to pass through. But network ACL is stateless in nature, and it will check the outbound rule for that uh, response and allow based on the rule. And if it is allowed, then the response is routed back to internet gateway. So internet gateway again does the network address translation from private IP address to the public IP address, and sends it back to the requester. So this is basically a data flow from the requester to the instance and back to the requester. So this is called an inbound call. So let's understand what outbound call means. So outbound call is basically from instance within the VPC to the internet and back to the uh, instance. So let's go through the data flow of it. So each is to makes in the private subnet. If we have taken an example of private subnet here, so let's understand how these outbound calls are made through the private subnet, because instances in the private subnet cannot directly talk to internet gateway, right? So inbound call, if it's an outbound call, EC2 instances in the private subnet makes an outbound request using a NAT gateway. So EC2 instance sends a request to the internet. Security group checks the particular traffic is allowed. If it is allowed, then it goes to the network ACL of the private subnet. Then if it is allowed, then it goes to the router. So in the router, it checks the route table. When it checks the route table, it sees that anything, we have configured any request or all request, um, other than this local request should go to NAT gateway ID. So the request is routed to NAT gateway, and this, again you have uh, uh, a firewall here, check here. So that would be like there will be a network ACL which checks the request, and then it goes to subnet, sorry, security group there, then it reaches the subnet gateway, sorry, then it reaches the NAT gateway. Then that, you know uh, private IP is you know uh, translated, and that information is sent to internet gateway, and then back to then it is a then the request is sent to the internet, and the same process would happen, in a backward direction, and it would reaches the database server. So I have you can just go through these steps again if you find it difficult to understand at the first instance itself.